I'm going to present a theoretical work for acceleration mechanism of pickup ion in the solar wind by compressible plasma turbulence. Pickup ions are originally neutral interstellar atoms. They can pass through the heliospheric magnetic field close to near the sun, and when they do charge exchange with the solar wind ions, they become pickup ions. The original speed of pickup ions in the solar wind reference frame is exactly the solar wind speed. And on the right side, we show that the spectrum of a few ions, hydrogen, helium-1, and helium-2 spectrum in the solar wind in the spacecraft reference frame. The bottom, we show their spectra in the solar wind reference frame. As you can see, the soldier here is the pickup ions in protons, pickup ion in helium plus, and a little bit pickup ion in helium double plus. And there seems to be an exact, there is a shoulder that's exactly at the solar wind speed. However, if you look at it carefully, some of the particles actually go above the solar wind speed. And then by the time that when you reach significantly above that, there is a tail of particles. These are the accelerated pickup ions. Clearly, pickup ions are accelerated in the solar wind. They become superthermal tail in the spectra. Most times, we observe the superthermal tail have a power law. They have a p to the minus 5 distribution function. This is called a common spectrum of superthermal particles. The origin of this, the p to the minus 5 spectrum, is not clear. Fisk and Glagler suggest the acceleration of these superthermal tail particles using stochastic acceleration by compressible turbulence. This shows a smoking gun in the observations for this particle acceleration by compressible turbulence. In the top, we show the solar wind density and the solar wind velocity, and we take the solar wind density, calculate its time derivative, and this is shown in this black line. When there is a large change of solar wind density, and we often see that the thermal particles intensity is enhanced. When the density fluctuations is small, we see that the superthermal particle intensity tends to be low. Of course, the density fluctuations not only include compressions of plasma, but also include the convections of solar wind density gradient. According to Parker transport equations, every time energetic particles go through a compression region of plasma, the particle energy will increase. If the particles go through the cooling region or a solar wind expansion region, the particle energy will decrease. Of course, if the particle just goes through the compression zone once, it only gains a limited amount of energy. However, if the particles can diffuse going through the compression region repeatedly, then it can achieve higher and higher energies. This is the equation. Parker equation can describe so-called diffusive compressional acceleration. Here is a simulation. With this, we can ascribe a plasma wave, compressible plasma wave, with repeated compression and rarefaction. Eventually, it turns back, the velocity turns back to normal. With this model, we can compute the spectra of those particles. Once the particle goes through a series of compressible waves, compression and decompression, the spectrum of original pickup ions will become wider, and the acceleration on the positive high energy side, it developed a spectrum that eventually will go to the p to the minus 3 spectrum. On the lower side, the cooled particle side, the spectrum will tend to be flat. This spectrum does not depend on the magnitude of diffusion coefficient. The acceleration mechanism is very similar to diffusive shock acceleration. Every time the particle jumps across a compression region, it's going to gain energy. But the particle in compressible wave can jump several compressional zones, still gain energy. That's why diffusion coefficient is not important for the distribution function of accelerated particles, as long as the diffusion length is larger than one individual compression zone but smaller than the wave train. Often, in the solar wind, there is adiabatic cooling effect. With the cooling going on, the spectrum does not become p to the minus 3 spectrum. Instead, it's a steeper spectrum, depend on the balance of adiabatic cooling and the stochastic acceleration by compressible turbulence. Similarly, if there is a loss mechanism, the spectrum can also be steeper than p to the minus 3 if it's dependent on the balance between the loss and the acceleration. Acceleration by random plasma compression and decompression can be done perturbatively, and the final behavior of particle acceleration is equivalent to particle diffusion in momentum space. The diffusion coefficient by compressible turbulence, if the turbulence is well developed, and the diffusion coefficient should be proportional to the p to the square. With this, the accelerated particle spectrum will develop into a power law. The power law depends on the ratio of adiabatic cooling to momentum diffusion rate. The acceleration by compressible turbulence is fast, much faster than acceleration by aphinic turbulence. Because of this, the accelerated particles will build a power law spectrum, and then these particles contain momentum, energy, or pressure. And the pressure of these accelerated particles will build up quickly if the acceleration is strong. And eventually, the energies or the pressures will go above the solar wind pressure, and then that could have a dynamic effect on the plasma turbulence. The acceleration of particles increase the pressure of the total system. And assume that the pressure is made by the sound wave with WKB approximation, we can find that the wave amplitude of compressible fluctuation will be decreasing with the total pressure in the particles. And also the wavelength will also increase. The combination of that is that the particle acceleration will decrease with pressure. This shows the spectral slope of accelerated particles as a function of pressure of accelerated particles. Initially, when at the presence of a compressible turbulence, the amplitude, and then if it is small, so that the ratio of V over delta V is large, the particle will increase its spectral slope and the pressure as time's going on. However, because the amplitude of plasma fluctuation is small, the growth of pressure and the growth of spectral slope is only limited. If the plasma turbulence amplitude is large, so that the ratio is small, the growth of particle pressure and the growth of particle spectral slope will increase, and eventually the particle spectral slope can go above p to the minus 5, and at that time the pressure can increase dramatically as time goes on. If the pressure is too large, it can decrease the plasma fluctuation amplitude, and then eventually the amplitude decreases to so low and the spectral slope stops at p to the minus 5. And if it's the right amount of the plasma turbulence amplitude, the particles will increase its slope and increase its pressure to the right amount, so eventually it reaches the p to the minus 5 spectrum. Given the particle transport equation in the co-moving plasma reference frame, here is the diffusion of particle momentum and adiabatic cooling and the source. And with the equation, we can integrate the momentum to establish an equation for the momentum. It finds that the increase of momentum is proportional to the momentum itself. The solution to this equation is that the P will exponentially increase or decrease with time. If this quantity is positive, it will increase to infinity. If this quantity is negative, then it will decrease to 0. So when the balance occurs, that they have limited amount of pressure in the accelerated particles, that requires this quantity must be less than 0, so that when at the limit they are equal, and then you get the limited spectral slope, which must be greater than 5. The largest number is minus 5. So that's why the particles will automatically produce a p to the minus 5 spectrum if the system starts with a large enough compressible turbulence and the pressure can react and to the turbulence amplitude avoid the pressure explosion. Under this equilibrium, the particle transport can be written as this. In there, you have a balance of acceleration and a balance of adiabatic cooling. In the solar wind, compressible turbulence does not appear everywhere. Only limited volumes of space or time. So this shows the intermittent compressible turbulence, and you divide the particles, the space into the regions with acceleration and without acceleration. Of course, the particle loss, adiabatic loss, or other losses, if they are there, and then these two equations will also establish a power law distribution function, and we pick up then the maximum after you limit the total pressure of accelerated particles. The maximum acceleration rate can only be this large, must balance the effect of adiabatic cooling and other losses. These show the spectrum of accelerated and cooled pickup ions in the spacecraft reference frame, and varies of particle acceleration rate and cooling rate, and all of them establish a p to the minus 5 spectrum on the acceleration side. And compared to what is observed, here is the taken from the observations, and if it is in the acceleration zone, you get a p to the minus 5 spectrum. If it is in the non-acceleration zone, you also get the particles that come from the accelerated regions, and you also have the p to the 5. But this region probably it is enhanced particle due to the presence of other acceleration mechanisms. This is at 1 AU, this is at 5 AU, 5 AU at high fast solar wind, and this it has stronger, a steeper spectrum due to high cooling. But the spectrum has not developed an equilibrium with the cooling. The acceleration of particles by compressible plasma turbulence in the diffusion-dominated region is very fast. The behavior of acceleration is very similar to particle diffusion in momentum space, or second-order Fermi acceleration. With continuous particle injections, like pickup ions, all spectra will try to establish a power law distribution function above without adiabatic cooling. The power law index will approach to minus 5. However, if there are cooling mechanisms, the spectral slope will be steeper. The pressure of accelerated particles can build up very, very quickly. If the pressure can reduce the plasma turbulence eventually, then the p to the minus 5 spectrum can be maintained. At that time, the particle acceleration and particle cooling and other losses are balanced. In the solar wind, plasma compressible turbulence do not appear everywhere. They exhibit intermittent nature. In that time, the particles can, in addition, suffer a loss from escape of acceleration region, plus the addition other losses, adiabatic cooling, and other losses. Then the particle will establish with stochastic acceleration by compressible turbulence. In the end, it is easy and faster to establish a p to the minus spectrum if we start with enough plasma turbulence.